Hi, in this presentation we're going to discuss vibrations and waves. So when something moves back and forth, we have a vibration, and that's just a periodic wiggle in time. And then if we add space to that, that wiggle occurring both in space and time, we call that a wave. And waves extend from one place to another. We can have two different kinds of waves. We can have mechanical waves, and these are waves that need a medium to pass through. And when I talk about medium, I mean this wave has to move through air, it has to move through water or a solid object like a brick wall or something like that. And these are things like, say, sound waves. Sound has to move through air or water or whatever. Or the waves that we observe in water, like as we see here in this picture, as the drop falls and creates the wave spreading out. On the other hand, we have electromagnetic waves. And electromagnetic waves don't need a medium to pass through. So things like light and radio waves and X-rays, these types of waves can cross, for example, the vacuum of space. They don't need a medium to move through. Let's say if we wanted to get a picture of a wave, we could do that pretty simply. We could take a weight and we could tie it on the end of a string and hold that string up. And then as we move the weight back and forth, well, we've created a simple pendulum. And as that pendulum moves back and forth, we could have it maybe draw a line on a piece of paper, and then we would have a picture of a wave. And the time it took our pendulum to swing back and forth one time would be called its period. And if we lengthen the string of our pendulum, then we're going to have also a longer period. So let's say when we first made our pendulum, we had a string that was 1 meter long. We tied our weight to it and started moving it back and forth, and it had a certain period. Well, what would happen if we doubled the length of our string to 2 meters? Well, then we would actually double the period of our wave that our pendulum is making. And it's important to realize that the period or the time of that one to and fro movement of our pendulum doesn't depend on any way on the mass of the pendulum. So it doesn't matter if our pendulum is heavier or lighter or bigger or smaller. It only depends on the length of the string of our pendulum. So again, when we had our pendulum and we were making that drawing on a piece of paper, this is a visual representation of our wave, and we call that a sine curve. And we get these sine curves when we trace out the path of a vibrating pendulum over time. So we can see our pendulum starts from a midpoint, goes up, goes back and forth and back and forth. And we have that picture, that sine curve that shows us that movement of the pendulum. And you can do this by creating a pendulum, maybe making it out of a kitchen funnel and hanging it from a string. And as you move it, as you set the pendulum swinging back and forth, you can move a piece of paper underneath the pendulum, and as the sand comes out of your funnel, it will draw that nice sine curve on the piece of paper. We can also make these sine curves by setting, say, a weight bobbing up and down on a spring. So you can see here on the left we have our weight. He's attached to a spring. As we start it moving up and down, if we have a pin attached to our weight, it's going to draw the same sine curve on the paper as the paper is pulled past the pendulum. And it's really nice to have these visual sine curves to look at when we're talking about waves, because this can help us look at the different parts of a wave. So for instance, you can see the dotted line going through the middle of our picture here is kind of the midpoint of the wave. And when we look at the wave as it goes past the midpoint and goes to its highest point, we call that the crest. So right here at the top would be the crest of the wave. And then opposite that, as our pendulum keeps moving and creates our sine curve, we see way down here, the furthest point from the midpoint going down is going to be our trough. And as we have our crests and our troughs, the furthest it gets from that midpoint, that distance between the midpoint and either the crest or the bottom of the trough, is called the amplitude. So you can see here in this wave, whether we measure the amplitude from the midpoint to the crest or from the midpoint to the trough, it's going to be the same distance. And then we can also measure the wavelength of our wave. And you can measure the wavelength of a wave from any two identical points on two different waves. So for instance, in this picture, we can see they've measured from the crest of this wave to the crest of the next, and that gives us a wavelength. But we could also measure from the trough of this wave to the trough of that one and get the same wavelength. Or we can pick a completely arbitrary point, like say right here on the upswing of this wave, and as long as we pick the same point on the upswing of the next wave, we get the same wavelength. And no matter where we measure the wavelength from on these waves, as long as we measure from the same 2 points, or the same point on two different waves, the wavelength is going to be the same. Now, how often this vibration occurs, or how long it takes or how often our pendulum makes a swing to and fro in a certain amount of time, is called the frequency. And so the frequency specifies the number of to and fro vibrations in a set time. And usually when we're talking about waves, we're using 1 second of time. And so this would also be the number of waves passing any point per second. The unit we use for frequency is the hertz, and that's named after Heinrich Hertz, who is a scientist who researched acoustics and sound and vibrations. A frequency of 1 hertz is a vibration that occurs once each second. And when we were talking about our pendulums, mechanical objects such as our pendulums usually have a frequency of a few hertz. So if I take a pendulum and make it in our house and swing it back and forth, it'll probably have just a few hertz, maybe 2 or 3 hertz. So it would go back and forth maybe 2 or 3 times a second. But when we deal with waves, there's waves that have much, much higher frequencies. We can have waves with thousands of hertz, and we call those kilohertz. We can have waves with millions of hertz, megahertz, or we can even have waves with billions of hertz, gigahertz. So in each of these, for kilohertz, the wave is going to have a frequency, in the thousands. In the megahertz, it's going to have a frequency of millions of times per second. In gigahertz, it's going to have a frequency of billions of times per second. Most of the sounds we can hear, whether it's music or voices or a dog barking or any kind of noise like that that we hear, has a frequency of a few hundred or several thousand hertz. And that's pretty much the limit of our hearing. But if we look at things like, say, AM radio waves, those have frequencies in the kilohertz, in the thousands. FM radio waves have a frequency of millions, megahertz. And then the Wi-Fi we use to, say, connect our devices to the internet, Bluetooth, so that your phone can talk to your wireless speakers, or your cell phone, they operate at billions of hertz or gigahertz. And so a few years ago, for instance, the standard for Wi-Fi and cell phones was 3G or 3 gigahertz. Then it was 4G, and now we have networks and devices that work on 5G. So we talked about the frequency, which is how often in a set time a wave occurs. But we can also talk about the time it takes for a complete vibration, and we call this the period. And frequency and periods are reciprocals. So if we know the frequency, we can say 1 divided by that frequency will give us the period. Or if we know the period, we can say 1 divided by a period gives us the frequency. So let's say we have a pendulum that makes 2 vibrations in 1 second. What would we say it's its frequency? And we measure our frequency in hertz, and we know it makes 2 vibrations per second. So its frequency would be 2 hertz. And knowing this, we can figure out, well, what is its period? And its period would be 1 divided by 2. So its period would be 1/2 or zero point 0.5 of a second. And we can go back and check this out. Well, if the period is zero point 0.5 of a second or half a second, how many times in a second can this wave occur? And we can see it can occur twice, 2 vibrations, 2 hertz. So let's say a frequency of a particular wave is 20 hertz. What would its period be then? And we know that its period is 1 divided by the frequency. So its period would be 1/20th of a second. So when we talk about wave motion, it's important to realize that waves transport energy and not matter. So think about if you drop a stone in a pond, the ripples go across the pond, but does the water come out of the pond? No. No, once the ripples are gone, the water returns to its original position. Or if you've ever seen a wind blowing across a grassy field and you can see the waves actually move across the grass, but does the grass move? No, it's pretty much once the wave is passed, the grass returns to its original state. Same thing happens when we have a sound or disturbance in the air. The molecules in the air transport that energy, but the air is still there in the room after the sound wave is gone. We can also talk about 2 different types of waves. We can talk about whether the wave moves in the direction of travel or whether the wave moves perpendicular to its direction of travel. Let's look first at what we call longitudinal waves. And with longitudinal waves, the media that the wave is moving through is going to vibrate in the same direction that the energy transfer is moving. So in the same direction as the wave, that's going to be how the medium is going to vibrate. So let's look at this picture here. So if we set up this tuning fork vibrating, and as it vibrates, the tines of the tuning fork move back and forth. And let's say as the tine of the tuning fork moves to the right, it compresses the air and makes these compressions. And then as the tine of the tuning fork moves back towards the left, it kind of makes a stretched region, what we call a rarefaction. And so we have these, as the tuning fork vibrates, we have these compressions, rarefactions, compressions, rarefactions. And this is how a sound wave travels in, say, solid, liquid, or gas like the air. So sound wave is a longitudinal wave. The wave is actually vibrating in the same direction as where the sound is going. So the sound is going from left to right in this picture, and then the waves are actually being compressed left to right. We can also have transverse waves, and this looks more familiar like our sine waves that we talked about before. And in transverse waves, the medium vibrates perpendicularly to the direction of the energy transfer. So in this case, let's say we have a rope attached to a wall, and we're going to vibrate it by moving our hand up and down. So the movement of the energy, the direction of the energy transfer is going to be from left to right, as we can see in that arrow. But as we shake our hands up and down, we see the waves are going up and down. So the actual vibration itself is perpendicular to where the energy is moving left to right because the vibration is going up and down. We can also see this vibration if we shook our hand here side to side. Then the vibration would be side to side, but it would still be perpendicular to the movement of the energy going from left to right there. And we see this type of transverse wave in things like if you pluck a string on a musical instrument, a guitar or a harp or a violin, you'll see that vibration go from side to side. Radio waves and light waves, if we have, say, a star over here that's vibrating and creating light waves and radio waves, they are coming out from the star, but the actual direction of vibration of those radio and light waves will be perpendicular to the direction of travel. Excuse me. We can also determine a wave's speed now that we know a little bit about waves. And this describes how fast this disturbance is moving through a medium. And to calculate wave speed, we either have to know the wavelength and the period of the wave, or the wavelength and the frequency of the wave. So we know that the period is the time between one crest passing and the other arriving. We know if the frequency is how many vibrations per second, and the wavelength is the distance between crests and troughs. So if we want to find wave speed, and we know from going way back to our discussions on the laws of motion, if speed is distance divided by time, well, then how can we calculate our wave speed? And we could calculate our wave speed very simply by dividing our wavelength, our distance, by the period, which is the time. Okay? Or since period and frequency are reciprocals, we could also say that the wave speed would be the wavelength multiplied by the frequency. So we can use either one of those to get our wave speed. So let's say we wanted to calculate the wave speed, and we have a wavelength of 10 meters and a period of 2 seconds. So to calculate the wave speed here, it's pretty easy. We just have to divide our wavelength, 10 meters, by our period, 2 seconds, and we get a wave speed of 5 meters per second. And we also know that period and frequency are reciprocals. So we can say that our wave speed, again, is frequency times wavelength. So to find our frequency here, we know that it's the reciprocal of our period. Our period was 2 seconds. So our frequency is going to be a half a second. So we can multiply our wavelength, 10 meters, times 0.5, and we get, again, our wave speed is 5 meters per second. When two or more waves interact with each other, we can call this wave interference. And wave interference happens because the waves are in the same place at the same time. And we call this the superposition principle. And this says that the displacement due to the interferences of the waves can be determined by adding the disturbances produced by each wave. And we can have either constructive interference or destructive interference. So let's look at constructive first. So if we have two waves occupying the same space and time, and let's say their crests and troughs align. And so in this case, we would add the individual waves together, and we would see that if we have them aligned perfectly where their crests and troughs align, then they're actually going to double their amplitude. They're going to increase amplitude. But now if they're out of step and the crest of one wave overlaps the trough of another, then the parts of the wave can be said to fill each other up. And we would subtract the individual waves from each other and they would cancel each other out. So looking at this wave here, let's say the amplitude of this crest is 2. The distance between the midpoint and the crest is 2. And then the distance here between the midpoint and the trough is -2. And the same here, this trough is -2 and this crest is +2. So you can see if we add that together, they cancel each other out. So we'd have a wave of 0. We can actually see these interference patterns. Say if we have two vibrating objects, like two tuning forks, touch the surface of water, and they'll create wave patterns. Each vibrating object creates its own wave pattern. And then as these waves encounter each other, we can see that if the crest of one wave overlaps the trough of another, we'll have that destructive interference, regions of 0 amplitude or no waves. And then if the crest overlaps the crest of another and the trough overlaps the trough of another, then we'll have that amplitude, that constructive interference. And so when we can either say the wave is in phase with each other when they match up, or when they're out of step, they're out of phase. And you can see this in this picture over here. that as the waves match up, we have these lighter portions or constructive interference. Where the waves interfere with each other, we have those dark stripes or the destructive interference. We can also have something that's called a standing wave. So let's say we have a rope and we tie it to the wall. And as we shake the free end of the rope in our hand up and down, we create waves in the rope. And as the wave goes from our hand through the rope towards the wall, once it gets to the wall, of course, is too rigid or stiff to be vibrated by the rope. So the waves get reflected back along the rope, as you can see up here in this top picture. So we call the wave coming from our hand to the wall the incident wave. And then the wave that's reflected back to us is called the reflective wave. By shaking the rope just right, we can cause the incident and reflective waves to kind of be in phase with each other and create a standing wave. And when we have the standing waves, we have something called nodes, which are regions of minimal or zero displacement. So we can see the nodes here run right through the middle of where those waves go. And if you looked at the rope, you will see that as the waves go through the rope back and forth, that node hardly moves at all, or it doesn't move at all. But now we have our antinodes, which are regions of maximum displacement. So those guys are right here, kind of in the middle of the wave, where the rope has moved the furthest away from the midpoint, either the crest or the trough. So those would be the antinodes. And our antinodes and nodes occur equally apart from each other. So we have a node here, antinode here, node here, antinode here, etc. And so if you were, say, if you had a little bug that was on this rope, if the little bug was right there on the node, he would not notice any motion at all. He would not feel the waves going through there. He wouldn't even know there was a wave moving through the medium. But if the bug was on the antinode, well, then he would get quite the ride and he would feel the action of that wave quite a bit. And as we are shaking our rope, here we have the two standing waves, but we can shake it and get three standing waves, four standing waves. The faster we shake the rope, the more standing waves we can get. So again, if we shake the rope with twice the frequency, we would have two loops. Okay. So here we're shaking our rope and getting our standing wave. Here we have shaking it twice as fast, we get two loops. And then if we shake the rope three times as fast, well, now we'll have three loops. But notice that as we increase the frequency, our wavelength is getting shorter. So these two waves here in B are half the wavelength of the wave in A. And then the three waves in C are only 1/3 of the wavelength in A. So as we increase that frequency, we're shortening our wavelength. When we're dealing with waves, we also deal with something called the Doppler effect. So you might have been, maybe if you've been in your house or standing on the street and a fire truck or a police car with its siren on goes past you. And you may have noticed that the pitch of the siren seems to change as the vehicle approached you and then changed again as it went past you. So as it's coming towards you, the pitch seems to get higher, and then as it goes away, it gets lower. So, like say if you had like one of the European Nina sirens, it would go like Nina, 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 Nina as it's coming to you. And as it goes away from you, it go like Nina, 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 get lower. Well, what's going on here? Well, the Doppler effect occurs because objects create waves. So let's say we have a stationary object that's vibrating and is creating a wave. And the waves spread out from that object in all directions. And the waves all have the same wavelength. So a person standing here at site point B would hear the same thing as a person standing here at point A. But now let's say our source of sound is moving towards A. And basically, now the sound source is chasing the waves it's produced. And you can see it kind of compresses the waves and increases their frequency. So A perceives these waves as coming more often at a higher frequency. So the sound that A hears would be at a higher pitch. And you can see if B here, as the source of the sound is going away from B, they perceive the waves coming less often. There's more space between the waves, so they would perceive it at a lower pitch. This Doppler effect also applies to light. When a light source is approaching you, the light shifts towards the blue. When the light source moves away from us, it shifts towards the red. And we can actually use this in astronomy, say if we're looking at a distant galaxy, and we can tell whether the light is shifted towards the blue, meaning the galaxy is coming towards us, or if it's shifted towards the red, meaning that distant galaxy is actually moving away from us. Or we can even look at a distant star and say, well, which way is this star spinning? Is it spinning clockwise in relation to us or counterclockwise? And we just have to see, if we look at the right hand side of the star, is it blue shifted or red shifted? And the same with the left side of the star. And for instance, if the right hand side of the star is blue shifted and the left is red shifted, then we know that that star is rotating clockwise in relation to us. So what happens if our source of vibration starts moving as fast as the waves it makes? In this case, we've gone pretty much past the Doppler effect. And what happens here is the waves start to superimpose directly on top of each other. So as the object is moving faster and faster and catches up with its own waves, now as it produces the waves, it's right there where it's being produced. So this kind of creates kind of a wall on this side where the object is moving. And as the object keeps moving faster and faster, we start to see this kind of uh, cone or arrow-shaped form of overlapping waves created. And the faster the object goes, the narrower the angle of this arrow shape of overlapping waves. So let's say here, the velocity of our object is still less than the velocity of its waves. And so here we can see we would have that Doppler shift effect if we were standing over here or over here. Now the velocity of the object is equaling the velocity of its waves, so we're starting to get that bow wave effect. Here, the velocity of the object is more than the velocity of the waves. So the object is actually out in front of the waves it's making. And then as it keeps moving faster and it's greatly exceeding the velocity of its waves, we can see that that angle that's produced by where the overlapping waves meet is going to get much more acute. And just to say an object can create that bow wave in water, objects traveling in air can create these same types of waves, but we call them shock waves in air. In water, it's two-dimensional. Think of a boat on a lake. The bow waves come from the front of the boat and keep on going till they reach the shore. But in air, this shock wave is three-dimensional. Again, so in water, the bow wave forms a V or an arrow shape that spreads until it reaches the shore. In the air, the shock wave is formed by overlapping spheres, and these spheres form a cone that stretch from the object, and those spheres will keep spreading until they reach the ground. And if we have a plane that can fly faster than sound, a supersonic plane, it's actually creating two cones. It's creating a high pressure cone generated at the front of the plane, and then another low pressure cone that's kind of following at the tail of the plane. Between these two cones that are created at the front and the back of the plane, the air pressure is going to rise very quickly above normal and then fall very quickly below normal atmosphere as the plane passes. And this sudden overpressure followed by that under pressure is what we hear as a sonic boom. And the sonic boom is a continuous event as the plane flies. When I was younger, my father was in the military, so we grew up on military bases. So I was very familiar with sonic booms as the planes were flying overhead and they reached supersonic speeds. We'd hear these sonic booms all the time. And if you've never heard one, they're quite loud and they would rattle all the windows in the house and everything like that. To us on the ground in our house or whatever, it sounded like a single event, just boom, and it was over. But that boom actually travels with the plane as long as the plane is flying faster than the speed of sound. So look at this picture here. So this person at sea, as the plane flies to the left, well, they've already heard the sonic boom. The sonic boom as it travels and meets the ground is now being experienced by person B. And here's person A. They have no idea what's going on. They might see the plane up here, but they haven't heard the sonic boom yet. It's also important to realize that sonic booms aren't produced by the noise of the plane itself. They're actually just produced by the rapid compression and expansion of the air, those shock waves that the plane is creating. So a silent plane, a plane that made no noise, as long as it was going faster than sound, would create the sonic boom as well. And we can have sonic booms from things like, say, supersonic projectiles, and also, say, the tips of whips. If you saw like Indiana Jones in the movies where he cracks his whip, what's actually creating that crack is the tip of the whip moving faster than sound. The sudden overpressure and then under pressure is what we hear as the crack of the whip.